Good morning. Did not take time to do. I did not take time to do minute drill or fluency today. So go ahead and try to get your practice to load up. Give you a few minutes. Paper, pencil. You need the calculator. You should have got it on your way. You walk through that door, blue and white. All right, so give you a few minutes to go ahead and try to log in school with you. Get your hoods off. Morning, William, Destiny.
Good morning.
Good morning.
Aaliyah. I do it every time. Huh? You say what? Say what? Somebody said that's fine. I'll do. Which I didn't even notice until last week. I'm gonna give you a few minutes to see if your practice wheel low. It does show our standard already. Give you a few minutes. I'm gonna write to the 5. Huh? What's today? What's today? Okay. It should say Monday, March 1st, though. Or March 1st. Okay, that's the one. I need to go back and put Monday in front. Who was in the class on Wednesday, Thursday, like you supposed to? You want me to have it today, yeah? You want me to have it? Okay. Monday, Wednesday, Thursday? Anybody in the class from home? Remember those your virtual days. What we talking about? That was Monday, Tuesday.
No, we talked about impossible and more than likely. Yes.
Good. And all of that dealt with probability. So today we are still looking at probability. SP 7A and 7B, it says I can find experimental and theoretical probabilities with 60% mastery. So on Wednesday and Thursday, we began looking at probability. Today, we're going to continue to look at probability, learn the difference between the two. As always, remember that you are a champion. Regardless of the situation, it's raining in the morning, we didn't want to get up. We're going to be some math champions today. All right, vocabulary. Experimental probability is the probability of an event based on the results of an experiment. If I have a coin, what are my two outcomes? Heads or tails. If I was to flip that coin more than once, I then have an experiment because I have done it consecutively. That's the difference. Theoretical probability is what you would expect to happen in an experiment, which will be used to find the likelihood of an event. So experimental probability is what happened when I did that experiment 25 times, and then theoretical probability is what should happen without me doing the experiment. That's the major difference. When I do that experiment, I get something that's known as a sample space, which are all the possible outcomes for that experiment. What's going to happen? All right, and then we have something known as uniform and non-uniform. Uniform means each probability is equally likely, and then non-uniform is not equally likely. If I have a coin, I only have two outcomes. So that means I have 50% chance of getting heads, 50% chance of getting tails. So that would be a uniform probabilities because I can get half and half. As you notice the difference between the two, we are writing a fraction. Fractions are the same way as you learned back in 4th grade. The numerator will represent the part or how many times, and then the denominator represents the whole, or in other words, the total. So it works the same. On Wednesday and Thursday, we learned that after we write the fraction, we then divide it out and get a decimal. Then we'll shift 2 times to get a percent, and that will be our probability. Any questions about what we're doing? Fraction, change it to a decimal, get the percent. Questions about it? We think we can do it. All right. Your practice loaded for today? That's your practice loaded? All right, good job. What it have it having it is a math lab, paper, pencil. Y'all know my motto. If I can't see it, it's wrong. So if you type it, make sure you can type everything you need. All right, number 1, a frozen yogurt shop sells only chocolate and vanilla frozen yogurt. A says the owner expects that customers will be equally likely to order chocolate yogurt as vanilla yogurt. Based on this assumption, what is the theoretical probability a customer will choose vanilla? How many things we talking about? So that means 2 would be my what?
Denominator.
Good job, that is the denominator. How many times can I get vanilla? All right, you see we got 2 things. One is vanilla. What's a half? We need the decimal to get the percent.
0.5.
Good job.
0.5.
Shift 2 times to the right. Shift your decimal 2 times to the right.
100%.
Look again, 2 times to the right. Thank you. Fill in missing places with a placeholder. So that means the theoretical probability of getting vanilla yogurt will be 50%. Any questions about how we came up with 50%? Yes, no, maybe? Say yes, you need to know why? All right, we got 2 different yogurts. So 2 is the denominator, 1 of those is vanilla, so that'll be 1. 1 out of 2 is 0.5. Shift 2 times, 50%. All right, part B says on average, 70% of customers order vanilla yogurt and 30% order chocolate yogurt. In the following random number table, numbers 00 through 69 represents vanilla yogurt and numbers 70 through 99 represents chocolate yogurt. It asks, what is the experimental probability that the next customer will order vanilla? What do they tell us represents vanilla in this table? Vanilla?
0069.
00 through 69. So we need to count every time we see 00 through 69. All right, we can look at the first column. Somebody tell me some numbers.
02. 26 and 17. 32.
Get you one more. Okay. All right, second call.
19.
All right, keep going.
27. 35 and 23. 27. 49. 59. 09.
Two people can tell me number between 0, 0. Everybody in here got an average over 70 and above? Okay, so that means your mouth need to be bumping. Participation points, you need it.
$18. 63 and 64. 22. 33. 69. 32. 45. 58. 42.
Good. You don't get out of math by looking good. Come to school every day. That ain't gonna help you out of here. I need you to learn some math. The only way we learn math is to actually do the math. That means she counting. That means I need to be counting to make sure I'm gonna get the same number they get. Because if I don't, I need to see what it is I'm doing wrong. That's what I'm here for. That's why I ask you got questions. Don't sit here just looking at me and then you got kids reading and then I'm sitting there just waiting on somebody to give me an answer. Don't do that. All right, so how many times or how many numbers do we have circled?
33.
Right out here, 33. Somebody verify.
33.
All right, how many total numbers do we have? 99. No. All right, I hear 50.
50.
All right, so Amir verified it. All right, somebody divide it out.
$0.66.
0.45. Shift 2 times.
66%.
Percent, good. So the theoretical probability before they did the experiment told them that they should have had vanilla about 50% of the time. And then after doing the experiment, they figured out that they had vanilla 66% of the time. So that's the difference between theoretical probability and then experimental. Any questions about it? All right, anyone still need anything? Okay. Number 2 reads, of the 32 students in Joe's class, 8 students ride their bikes to school, 5 walk to school, 4 get a ride to school in a car, 15 take the bus to school. Joe created a spinner that represents the breakdown of how each student travels to class. He spun the spinner 20 times and recorded his results in the table below. They asked, what is the experimental probability that the spinner lands on the section labeled bus? How many times did it tell us we landed on bus? 8.
8.
Total? Is it 20?
12. 20.
It was 20. I know they had it somewhere else. Somebody said, and I said, Then I went back and looked. 20. What as a percent? Good job.
40%.
Any questions about it? You got what? No, you don't have it. On a regular computer, it's on number 5. Shift to number 5. You see it? I don't know about the Chrome. You got y'all know me, I don't look at just an answer, so I hope you had your fraction, your simplified fraction, your decimal, and then your percent. All right, two spinners are shown. Which statement best explains why one spinner is more likely to land on a section labeled A than the other spinner? I'm gonna let you think about it. Why is one spinner more likely to land on A than the other spinner? Now notice, I don't look at answer choices first. I'm always look at my spinners and I'm gonna see what I notice. Do you notice anything about these spinners? All right, so if they got two A's, that means I may get there more, right? All right, so we already eliminate C and D because spinner 2 isn't more likely. And then why is spinner 1 more likely, A or B? Good job.
A.
Any questions about it? Y'all sure? All right, everybody got it? Sure, that was a multiple choice. All right, number 4. A family is planning on having 2 children. Assume that it is equally likely for each child to be a boy or a girl. Which of these statements are true? A says the theoretical probability of the first child being a boy is greater than the theoretical probability of the second child being a girl. How many genders do we have? So if I get a boy, what's my percent? I have. If I get a girl, what's my percent? I have.
I have.
Equally likely. All right, so A said the theoretical probability of the first child being a boy is greater than the theoretical probability of the second child being a girl. True or false? Why you say false?
They both are have.
Good job. All right, B said if the first child is a boy, the theoretical probability that the family will have a boy and a girl is equal to 1/2. Why you say no, Joseph? But is that how we look at it? All right, let me give you a visual. So they're saying the first child was a boy. And then the second child, they say, could be a boy or a girl. So they want to know what the theoretical probability the family will have a boy and a girl is equal to 1/2. So these are now our scenarios. This will be the boy and the girl. How many chances? 50. 1 out of 2. 1/2. All right, C says if the first child is a boy, the theoretical probability of the second child also being a boy is greater than the theoretical probability of the second child being a girl. Same scenario. Is 2 boys greater than having a boy and a girl? Nope, they are the same. D and D says if the first child is a girl, the theoretical probability that the family will have 2 girls is equal to the theoretical probability that the family will have 1 girl and a boy. All right, so I can have a girl, then I can get a boy, then I can get another girl. That will be correct. They will both be 50%. Any questions about it? Good job. As always, we move too fast, just say so. Of the 20 students in Kendra's class, 5 have black hair, 8 have blonde hair, 5 have brown hair, and 2 have red hair. Kendra used the spinner to find the experimental probability that this week's class leader will have blonde hair. She spun the spinner 15 times and recorded the results. What is the experimental probability that this week's class leader will have blonde hair? You said it was spun 15 times. Y'all agree? All right. Somebody give us the decimal.
0.6.
All right. So the percent.
60%.
Good job. Any questions on it? And I said probability is one of the easiest things we'll do in the 7th grade. Right, as a fraction, divide, get the decimal, shift 2 times, get the percent. Any questions about it? All right, number 6. 1 out of every 3 boxes of cereal has a prize in it. To find the experimental probability that the next box he buys will have a prize, Joe rolls a number cube 50 times. He lets a multiple of 3 represent a box with a prize and all other numbers represent a box without a prize. His results are shown in the table to the right. What is the experimental probability that Joe's next box will have a prize in? What did they tell us will represent a prize? Multiples of 3. Do we have any multiples of 3 over there? Somebody said 6.
Yes.
We only look on this side. I'm gonna roll right now. Is that the only multiple of 3? Multiples start at that number. So that'll be 3, 6, 9, 1 not in there. So we got 2 multiples of 3, 3 and 6. So then I ask myself how many times for each and add it up.
We added up the number of times.
Y'all said 3 and 6. So then how many with 3 and how many with 6?
20.
And then what's our total? All right, simplify 20, 50. And notice they kept it as a fraction. That's why I said simplify. What do 20 and 50 have in common?
10.
2 over 5.
Largest. Divide both by 10. 205. Good job. Any questions about it? Y'all got it? All right, 2 spinners are shown. They said choose true or false for each statement below. All right, look at those statements. Look at A first. Somebody tell us if you're thinking true or false and tell us why. Why you say false? You need to talk louder than that. I can't hear that.
Because B got more numbers than A.
All right, what's the probability on B then? You said 2. How many total? You said 2. How many total? Okay, so B had 2, 6, and spinner A had how much? Thank you, ma'am. All right, what about B? Why you say false?
Because the odds of spending 4 on spending B is going to be more than 1/3 because 2.
2 out of how many? Can 2 6 be simplified? To what? Simplified before you get to saying yes or no. All right, look at C. Why say true? On what? All right, you said it got 2 odd, 2 even, so there's 2 out of how many?
One half.
Told y'all I'm real slow. You gotta give it to me. All right, look at D. All right, somebody said false. Why you say false?
Because the amount of three, I would say three take up all spinner A bigger than spinner.
How you know it's spinner? Bigger. I need better than that. Why you say false? Don't tell me bigger. All I know is numbers and fractions. And now if you say on B it had such and such and on A it had such and such, then I can see a difference. But just telling me it's bigger, that ain't telling your classmate nothing. Some of them ain't opened their mouth yet, so you know they lost. How many threes? And how many on A? What is 1/6 to 1/4? Is 1/6 greater than 1/4?
No.
Nope.
No.
A lot of your friends want to say yes because the denominator is bigger. But if you look at your pieces, and we said the larger the denominator, the smaller the pieces. Got. Make sure you got false, true, true, false, and you do need your rationales that we gave, your equivalences. Should be in there somewhere. Any questions about it? All right. Anybody still need some? This one had 2 parts. I'm making it really small. Tonya wants to know the probability that a family with 3 children has 2 boys and a girl. She modeled the problem by tossing 3 coins at the same time. She let heads represent a boy and tails represent a girl. The results of her 20 tosses are shown in the following table. Part A, what is the experimental probability that a family with 3 children will have 2 boys and 1 girl? Now, how did they tell us we can identify them? H and T. H is for which one?
Heads represent boys.
All right. So that means before I even get started, I'm gonna identify what I'm looking for, H and T. And then they told us we're looking for 2 boys and 1 girl. So that means we need 2 H's and 2 T, 1 T. So if you see one, tell me which trial it is. They got 3 H's. We need 2 H's and 1 T.
2.
4.
They got 3 H's. That means they don't have a girl.
1, 5,
Try 1.
3.
Try 4.
Try 12.
Trial 17.
Try
Trial 20.
18.
All right, any others? 2 H's, 1 T. That's all of them. 8 got 2 T's, 1 H. All right, so how many do we have?
9.
Y'all look closer again. This big old
8.
we go together. 8.
8.
All right, 8, and we
8.
know we got 20 times. Somebody go ahead and divide it out. What is that as a percent? Good job.
40%.
So that's the experimental probability after they did that experiment. They then asked us to find what's the theoretical probability of 2 boys and 1 girl is 3/8. So they want to know, how does the experimental probability compare to the theoretical probability? Compare, are they in the same format? Right now, can I compare them the way they are? All right, so what do I need to do? Simplify. What's 3/8?
0.375.
I take it they was sleeping here. Then if I shift over 2 times, what do I get? Just 37? Yeah, give us all of it. So 37.5%. They told us to compare it. So the theoretical probability is 37.5, and then the experimental was 40%. Somebody give me a comparison. How do I compare? What do I look for when I'm comparing? Math has 3 comparisons.
Greater.
Greater than, less than, or? Okay, so what would I say about 40 and 37.5?
40% is greater than
40%,
37.5%.
40% representing which one, experimental or theoretical? Good job. Somebody can read. Somebody said the wrong one. So the experimental probability of 40% is greater than the theoretical probability of 37.5% of having 2 boys and 1 girl. Good job. All right, everybody got it? All right, let me know when you finish. All right, type in none decrease. We got it? All right. You spin a spinner with 4 equal sections labeled A, B, C. Which statements are true? A says the theoretical probability that you will land on A is twice the theoretical probability that you will land on C. True or false? True or false? Why you say true? 2 A's, what that mean? Two out of how many? Okay. And then what was the chance of C? So that means dog, you that still sitting there looking stupid, waiting on somebody to give you an answer. Common sense would at least tell me to find my probabilities and compare. All right, what B word? Why you say true? Good job. I got 1 B, 4 total. What C word?
No.
All right, it was 2 of them. All right, what D word? One divided by the 4 pieces we got is 5. Exactly. So they're saying Kennedy gonna do that experiment. She gonna get C 5 times. You gonna do that experiment, get C 5 times. Can I say that?
No.
So the one thing that's messed it up was the word exactly. Now, if they would have said about 5 times, then yeah, we could have went with that. All right, 10. A spinner, a number cube, and a coin are used to model an experiment. The spinner has 4 equal sections labeled 1, 2, 2, and 3. The faces of the number cube are 1, 1, 2, 2, 3, 3. On the coin, heads represents an even number and tails represents an odd number. A says the probability of an even number is the same on the spinner as it is on the cube. How many even numbers on the spinner? 2 out of how many? All right, how many on the cube? Out of how many? Is that the same?
No.
All right, B says the probability of an even number is the same on a coin as it is with the spinner. From part A, we know the spinner had 2/4. What's the chance of getting an even number on the coin? 1/2. Would you say they're the same? Why do you say yes? 2/4 simplifies to 1/2. All right, C says probability of an odd number is the same on a coin as it is on the spinner. What's the chance of odd on the coin? Coin only got 2 options. So either option, what's my percent?
Half.
How many odd on the spinner?
2/4.
That half is same as 2/4. Yeah, we said it from the last one. All right, they said the probability of the odd number is the same with a coin as it is with a cube. With the coin, we know that's 1/2. How many odd on the cube? 4 out of 6. Would you say that's the same?
No.
Good. Any questions about it? Anybody see a lead anything? All right, let me know when you get it. Just how many more? 3? We're gonna try to make it through them 3. My person who said you didn't have it, you got it? All right, 11. A family has 3 girls. The family toss a coin to represent the likelihood of a girl if they have another child. They let heads represent a girl and tails represent a boy. The table shows the results of their experiment. If the family has another child, predict whether the child would be a girl. So now they want us to do a prediction. Before we can make that prediction, what might we need to find? Good job. What's the probability of choosing a girl? 8 out of, somebody said 12, add them both to get the total. 40%. So what's our prediction? Can we predict that this family will have a girl next? I need more than just telling me they got more boys. I go with that one, myself. Predict the family will not have a girl because the probability was less than a half. So anytime you're doing a prediction, definitely make sure you relate it somehow back to what their probability was. Just telling them they had more, put in there how many more or what was the exact percents and values. All right, well, I got 12 up. Serena is playing a game with a number cube. To win the game, she must roll the number 4 on her next roll. The table shows the number of times she has rolled each number so far. What is the probability that she will win the game? How did they tell her she can win? So that means I'm gonna look for rolling a 4. What she got? How many times did she roll a 4? How many total? Somebody verify? All right.
24.
Divide it out.
.20.
All right, shift 2 times. And we can say about 21%. That's a small percentage of winning. All right, any questions on these 2? Anybody still need anything? All right, my yeses, let me know when you finish. We got 2 minutes to squeeze in the lab. Some of us done learned something today. All right, anybody else still get it?
Is that 21 or 20%?
21, about 21. Did you say you still getting the towel? Okay. All right, Raphael tosses a paper cup and records how the paper cup lands. The table shows the results of his experiment. Predict whether the paper cup will land open and down on his next toss. Use probability to explain your prediction. All right, they asked us about opening and down.
4,
Out of how many?
20, 20%,
All right, now give us a prediction. That ain't your prediction. That's the data. So if the data told us 20%, is he gonna have it open and down, or is it gonna be something different? So I predict that Raphael will not land open and down because the probability was only 20%. And that is the final question. So that means everybody should be doing what today? Everybody should be submitting. It was on the page with 11. 14 tell you to upload your work. So you got some paper of your work. You can take a picture and upload it right there. Get your belongings. All right, everybody got it? All right, everybody, including you at home, you should be submitting these on today. If you miss anything due to Wi-Fi or anything, I will be posting the recording. It's always usually after the buses leave, but I will post it so you can go back and get anything that you missed. And definitely make sure you submit today, if nothing else. I will remind you, you have 2 weeks to get all your work for 39 weeks complete. That's from January to now. You have until March the 12th. That's next Friday. Take care of your business. Have a good Tuesday.
have a good day.
You too, Destiny. Was that the one open in? Is that the one open in or Serena? Take a picture. Stay home. Tonight at home, take a picture. Send that picture to your email. Save it on your computer and then pop up in your. No. So just wait to submit. Don't submit the check. Wait to submit it. Nope. Send that a message in school. But see, I don't never check my email when I'm grading. And then I tend to forget. Somebody sent me something to my email, so that's why I say you send it as a message in school or put it in there. That way I'm guaranteed to get it. All right, let me show you. I should look it up. You would go to in your thing, go to members. And then where it has my name, it'll let you have an option to, it'll look like this. And then just click on send a message. And then the message is similar to the others. It'll have that little picture thingy for 5. That's how you're able to find your picture.
Miss Catchings, do we need to log out right
Yeah,
now?
you good with it. Y'all good.
Okay.
Got y'all still in there. Y'all have a good one.